Here's a very simple demonstration. In fact, the only equipment it requires is a ball. Even so, it's a very important demonstration because it illustrates a principle of physics that, if it had been discovered 2,000 years earlier, could have actually changed the course of science. Okay, so here's the question. I'm going to drop this ball, but before I drop it, I'm going to walk with constant velocity. So the ball will be moving horizontally with constant velocity. I'll release it. The question is, where will it land? Will it land right by my feet, behind me, or in front of me? Well, let's try it out. I'll start walking, get up to constant velocity, and then drop the ball. Well, I think you can see that the ball landed right by my feet, not behind me, not in front of me. So the answer is 1. The ball lands near my feet. In fact, let's take a look at it in slow motion. I think you'll see in the slow motion replay that as the ball accelerates downward, it continues to move forward in the horizontal direction with me. That really is the key point. Let me put it to a bit more of a test. I'll increase the velocity a little bit. Jog, drop the ball. Still, it lands right at my feet and comes back up. It doesn't land behind me or in front of me. So Newton's first law says that a body in motion will tend to stay in motion unless a force acts on it to change that motion. Now, in this case, as I move forward, I'm holding the ball, but I'm not exerting any force on it. When I let go of it, it just continues moving forward because there's no horizontal force acting on it to stop it from moving forward. So it just continues as it was before. So it moves forward with uniform velocity, moves downward with an acceleration due to gravity. When you combine those two motions, you end up with a path that's a parabola. And again, we can see that in the slow motion video. If you trace out the motion of the ball, it's a parabolic path, just like the parabolic path of water fountains and volcanoes erupting and things like that. Now, according to Aristotle, what would happen was the following. Aristotle said that to move a ball, I have to constantly exert a force on it to make it move. And if I let go of it, there will no longer be a force on it, and it will stop moving, and therefore it will land behind me. Well, that's not what happens. And in fact, I'm sure that argument sounded plausible to Aristotle and to others at his time. But if they'd just done a simple test like this, they could have seen that that wasn't the case. If they had tried that out, they may have actually discovered Newton's first law of motion 2,000 years before Newton did. Perhaps if Aristotle had had a pair of roller skates, maybe that would have helped him to determine the correct behavior of nature. Let's give it a try.
Here I have a low friction cart with an accessory on top, a little spring-loaded launcher. When I put a ball inside and it comes to this point, it shoots the ball straight up. Now, the question is, if I set the cannon and give this a nice push so it moves at a constant velocity towards the trigger, where will the ball land after it is fired out of the cart? Will it land in front of the cart? Will it land back in the cart? Or will it land behind the cart? So as you can see, the ball landed back in the cart. Why did it do this? Well, when the ball left the cart, it had the same horizontal velocity, v, as the cart. While it was in the air, the only thing acting on the ball was gravity. That was only acting in the vertical direction. Gravity was not affecting the horizontal speed of the ball whatsoever. So while the ball was in the air, its horizontal velocity did not change, and therefore it landed back in the cart. So here I am up on a 12-foot ladder. I have two bocce balls. What I'm going to do while I'm up here is I'm going to throw this bocce ball straight off to my side, while at the same time drop this bocce ball straight down. But the question is, which ball hits the ground first? The one that I throw off to my side, the one that I let drop straight down, or they both hit at the same time? So as you can see, they both hit the ground at the same time. Well, how'd this happen? Well, after I let both balls go, the only thing acting on them was gravity. Therefore, they both fell at the same rate. It didn't matter that I gave one ball some component of velocity in the horizontal direction. That's not affected by gravity whatsoever. Only motion in the vertical direction is affected by gravity. Therefore, I could throw the ball as hard as I wanted off to the side, and it would still hit the ground at the same time as the ball that I dropped straight. Here I have a low friction cart that has an accessory mounted on it, which will shoot this ball vertically when it reaches this trigger. Just like so. It falls back in the cup here. Now, with this experiment, I'm going to raise this end of the track and let the cart roll down the ramp, firing the ball when it reaches the trigger. Question is, where will the ball land after it is shot out of the cart? Will it land in front of the cart, back in the cart, or behind the cart? So as you can see, the ball landed back in the cart. Even though the cart was accelerating down the ramp, and the ball, once it left the cart, had a constant velocity v in this direction, it was still shot forward with enough of an angle that it could land back in the cart. Here I have a spring-loaded cannon, which fires a projectile like this. Now I have the cannon set to 30 degrees, and I have a basket at the other end set at 30 degrees, and it is set at the correct distance. So if I set the spring and fire, it lands in the basket. Now I'm going to change the angle of the gun to 60 degrees. And fire the projectile again. Now the question is, will the projectile land in the basket? Will it fly over the basket? Or will it land short? So as you can see, it landed in the basket again. This is because when dealing with projectile motion, if you're working with two different angles whose sum equals 90 degrees, they will land in the same spot. So if you fire a projectile with the same velocity at 30 degrees and 60 degrees equals 90, they'll land in the same spot, 20 and 70, 10 and 80, so on and so forth.